So welcome to the video. Today we're going to take a look at how to do a simple linear regression analysis on version 31 of SPSS. So we usually use this analysis when we want to investigate whether one continuous variable can be used to predict values of another continuous dependent variable. So for this example, we're going to look at whether how long people look at their screens each day is predictive of how stressed they feel. So here we have the number of hours they look at their screens each day, and here we have a stress score for each of the participants. And so we have about 100 participants in the study. So let's take a look at how to put these data into SPSS. So the first thing we're going to do is go down to variable view, and then we can give a name to our predictor variable. So let's call that screen time hours. So I'm using underscores here between the words because I can't use spaces. And then we're going to give a name to our outcome variable, which in this case is going to be stress score. So I'm using the words predictor variable and outcome variable. Sometimes people will use the words independent variable and dependent variable instead. So once we've done that, we can go over to the measures column and we can tell SPSS that both of these are scale variables, which is another word for continuous variable essentially. Next we can go down to data view and we can see that the names of these two variables appear at the top of these two columns. So then we can just go back to our Excel file, and if I select the top left piece of data and then I go down to the bottom, and whilst holding shift I select the bottom right piece of data, I can then go to Command or Control C to copy those data, and then I can click the top left cell in SPSS and I can go to Command or Control V to paste those data in, or I can go up to Edit and then down to Paste. So this analysis has a few assumptions. So one is that there is a linear relationship between the predictor variable and the outcome variable. So I've mentioned in brackets how we can check each of these assumptions. So for this one, we're going to create a scatterplot and we're going to see whether the dots or the data points are well represented by a diagonal straight line. So we'll start off by looking at this assumption, and we can actually check all of these other assumptions as we're running the analysis itself. So let's begin by creating a scatterplot. So we can go up to graphs and then down to scatter stroke dot. Then we can keep this simple scatter option selected. So we can go to define, and then we can transfer our predictor variable to the x-axis and our outcome variable to the y-axis. We can then go to OK, and that generates the scatter plot for us. Already we can see that we have a nice diagonal band that would be well represented by a straight line. Another way in which we can see that this assumption is met is by having a band going diagonally in this opposite direction. If we double click on this, we can open the chart editor, and then we can go up here where it says add fit line add total. And if we click that, it's going to put a line of best fit through the data points for us. And so we can see that, yeah, these dots are very well represented by the straight line, which supports the assumption that there is a linear relationship between the predictor variable and the outcome variable. So these other assumptions we can check whilst running the analysis. So we can do that now. So we can go up to Analyze and then down to Regression, then across to Linear. We can then transfer our predictor variable to the independent box and our outcome variable to the dependent box. If we click on statistics and then on Durbin-Watson, we can request that test. And as we can see here, the Durbin-Watson test relates to this assumption that the residuals are independent. This next assumption that there is homoscedasticity, we can check by creating another scatterplot. So to create this one, we can go to plots, and then we can transfer zpred to the x-axis and zresid to the y-axis. We can also take this normal probability plot option, and that relates to another of these assumptions, that the residuals are normally distributed. And we're going to go to continue and then to save, and we're going to check cooks, and that's going to check another of the assumptions. So the assumption that there are no influential cases biasing the model. And once we've done all that, we can just go to OK to run the analysis. So let's start off by checking those assumptions. So here we have this model summary table, and we have this Durbin-Watson column where we have a value of 2.029. And as we can see here, we want this value to be between 1 and 3. And since our value is, it suggests that the residuals are independent. Next, we can check this homoscedasticity assumption. So we're going to look at a scatter plot that we've just generated, and we're going to see that our dots are in a band. So what we want to see is that we have something like this, where we don't have a very obvious triangle shape within the data. So that one looks fine. And next we're going to take a look at the assumption that the residuals are normally distributed, and we're going to look at the normal probability plot, and we want to see that the dots follow the line. So we're looking at this plot here, and we can see that the dots very closely follow the line, suggesting that this assumption has been met. And the last assumption is that there are no influential cases biasing the model, and for this we used Cook's test, and we want to see that we don't have any values above 1. And so for this we actually look at our data file where SPSS has created an additional variable for us, and we can see that none of these values in this column are above 1, suggesting that that assumption has also been met. So that's how we check the assumptions of the test. Let's now take a look at how to interpret the results of the regression analysis itself. So if we take a look at this model summary table, we can see that we have an R-square value of 0.665. And if we just round that to 2 decimal places, we have a value of 0.67. And then to convert this to a percentage, we can just move this decimal point over 2 spaces, which would give us a percentage of 67, suggesting that the model explains 67% of the variance in the outcome variable. Additionally, if we look at this ANOVA table, we can see that we have a sig value of less than 0.001, and as this is less than 0.05, it indicates that the model explains a significant amount of the variance in the outcome variable. So that's essentially how we interpret the results of the linear regression analysis. But let's take a look now at how we can report these results, including the assumption checks that we performed. So we're going to start off by saying that a scatter plot indicated that there was a linear relationship between the predictor variable and the outcome variable, and we're assuming that we would include this scatter plot that we created as an appendix. So next we've said that a Durbin-Watson statistic of 2.03 supported the assumption that the values of the residuals are independent. And as we saw before, that comes from this model summary table and from this Durbin-Watson column where we have a value of 2.03 if we round that to 2 decimal places. Next, we've said that a scatter plot was created to assess the assumption that the variance of the residuals was constant, which is otherwise known as the homoscedasticity assumption. And we said that the plot did not indicate a violation of this assumption. And again, we've assumed that we would include that plot as an appendix. So in that case, we're referring to this plot here. Next, we've said that a PP plot was created to assess the assumption that the values of the residuals are normally distributed, and the plot did not indicate a violation of this assumption. And again, we've assumed that we would include that plot as an appendix. So that's this plot here, and we saw that the dots follow the line nicely. And then regarding the last assumption, we've said that Cook's distance values were calculated to ensure no influential cases were biasing the model, and all values were below 1, suggesting that no cases were biasing the model. And that's based on looking at this column here and checking that none of these values are above 1. So then we've gone on to reporting the results of the regression analysis itself. And we've said that a simple linear regression analysis using the enter method was conducted to examine whether stress can be predicted by screen time. And we've said that the model was significant, and that it explained 67% of the variance in the outcome variable. So let's just take a look at where all of these numbers come from. So we start off with some degrees of freedom values, 1 and 98, and those are coming from this ANOVA table, where we have a degrees of freedom value of 1 here in the regression row, and a degrees of freedom value of 98 here in the residual row. Next we have this F value of 194.71, and that is coming from the same table and from this F column where we have 194.706. So I've just rounded that to 2 decimal places. And we have this p-value of less than 0.001. So that's the same table, but we're looking at the sig column. And we have this 67%, so that's coming from this r squared value of 0.67. And as we saw before, that's coming from this model summary table and this r square column. So we've just rounded this value here to 2 decimal places. And finally, we've said that the regression coefficient indicated that on average, an increase in screen time of 1 hour corresponded to an increase in stress scores of 3.72. And so that's coming from this coefficients table. And I'm looking at this unstandardized B column, where we can see that in the screen time hours row, we have a value of 3.72. And so as we've said here, this indicates that every increase in screen time in terms of hours tends to correspond to an increase in stress scores of 3.72. And we can actually use this value in conjunction with this value here to predict someone's stress score if we know how many hours they spend on their screen every day. So this is what we would predict their stress score to be if they spent no hours on a screen every day. And then for every increase in hours, we can just multiply this value and add it to this value. So let's imagine that someone spends 10 hours on the screen every day. We're going to take this constant value of 11.65, if we round that to 2 decimal places. Then we will add to that 3.72 times 10, so that's 3.72 there, which gives us 11.65 plus 37.20. And if we add those two together, we get 48.85. So that's what we would predict someone's stress score to be if they spent 10 hours on their screen each day. So that's about it for the simple linear regression analysis on version 31 of SPSS. I hope that was helpful. If you have any questions, let me know in a comment and I'll try to get back to you. Thank you for watching and I'll see you next time.